Hello, this is Dr. Hanaa Assil, and this is paper 1CR of June 2022. So this is for the Pearson Edexcel IGCSE. The first question says the diagram represents an atom of an element. Use numbers from the box to complete the table. You may use each number once, more than once, or not at all. So the first thing he's asking about is what is the atomic number of this atom. Now, how do I know the atomic number? It is the number of protons. So if you see the key that he has there, the proton is the dark dot in the inside the nucleus. I have 4 of them. That means I have 4 protons. That means the atomic number is 4. Then he says, what is the mass number of this atom? How do we know the mass number? The mass number is the total number of protons and neutrons in the nucleus. So inside the middle of the atom, in the nucleus, you have 4 protons and 5 neutrons. That means a total of 9. That means the mass number is 9. Now, period number. How do we know the number of the period? You should know that the number of the period is the same as the number of shells. So how many shells do I have? I have 2 shells or 2 energy levels, the circles around the nucleus. That means this is in period 2. Number of electrons in the 2+ ion. What do we mean by 2+ ion? That means if this atom loses 2 electrons, what would be the number of electrons left? So, of course, it has a total of 4 electrons. If it loses 2 of them, then the electrons in the 2+ ion is 2 electrons. In terms of subatomic particles, I'm going to remind you that subatomic particles means the things inside the atom. Protons, neutrons, electrons. These are called subatomic particles. So he's saying in terms of subatomic particles, state a similarity and a difference for isotopes of the same element. Do you remember definition of isotopes? What do we mean by isotopes? They are atoms of the same element that have the same what? They have the same number of protons but different number of neutrons. So the similarity is they all have the same number of protons. Isotopes of the same element will have same number of protons, different number of neutrons. This question is about apparatus. Complete the table by giving the name of each piece of apparatus and a unit used for the quantity it measures. What is that first apparatus? You should know that that first apparatus is a gas syringe. It is used to measure volume of gases in centimeter cubed. So that's the unit. Now, what's that other one? The other one is a balance, and it weighs the masses or determines the masses in gram. The diagram shows apparatus used to determine to obtain pure water from sodium chloride solution by simple distillation. So this apparatus is for simple distillation. Remember, simple distillation is used to obtain pure water from a solution. Now, explain why it is necessary for water to flow continuously in and out of the apparatus. Remember that apparatus in the middle is called a condenser. I need water to go in from the bottom, come out from the top in order to do what? To cool and condense the vapor. So when you heat the sodium chloride solution, the water boils, the water vapor goes through the condenser. The water that surrounds it will cool and condense the vapor so that pure water is collected in the conical flask. Okay? Okay. Next, he says, describe a chemical test to show that sodium chloride solution contains chloride ions. Do you remember the test for chloride ions? Of course, the tests you should memorize. What was the test for chloride ions? Chloride ions, you need to add dilute nitric acid and aqueous silver nitrate. And if I have chloride, I will get a white precipitate. Again, test for chloride, nitric acid, and silver nitrate gives a white precipitate with chloride. Describe a physical test to show that the liquid in the conical flask is pure water. Remember, we have two tests for water. We have a chemical test and a physical test. The physical test is when we heat to boiling, and the water should boil at 100 degrees Celsius. So if it is pure, the boiling point is 100 degrees Celsius. What if it has impurity? You should know that if it is not pure, its boiling point will be a little bit higher than 100. So if it has impurity, like if it is instead of pure water, it's sodium chloride solution, then the boiling point will be 101, 102, 103, something like that. Okay? The third question says the diagram shows a chromatogram of the food dyes in 4 different food colorings, A, B, C, and D. So this is chromatography. And he's saying first, give the letter of the food coloring that contains 3 different food dyes. Remember, A, B, C, D go up and separate into different colors. So which one has 3 different colors? Can you see that B separated into 3 different spots, and that means it contains 3 different dyes. Give the letters of the 2 food colorings that contain the same dye. How do I know if they have the same dye? If they have spots the same height. So A and B have spots the same height, that means they have the same dye. Using the scale, and remember he has a scale there. Can you see the scale? 0, 1, 2, 3, 4. Determine the RF value of the dye in food coloring C. Can you see where C is? How do we determine RF values? Do you remember what is RF value? RF value is the distance traveled by the spot over the distance traveled by the solvent. Can you see that the spot went up to 2 and the solvent went up to 8? So the RF value is 2 over 8. RF value is distance traveled by spot over the distance traveled by the solvent. We measure from the start line or from the baseline to the spot divided by from the baseline to the solvent front. Give a reason why the dye in food coloring D moves the furthest from the start line. You should remember, chromatography separates the dyes based on what? It separates the dyes based on their solubility in the solvent. So if something like D goes up very high, that is because then it is the most soluble in the solvent. What if something doesn't go up? If it stays on the baseline, we say why did it stay on the baseline? Because it is not soluble in the solvent. So the one that is more soluble in the solvent will go up further in the chromatogram. Describe how a student could obtain a chromatogram similar to the one shown in the diagram. How do we do chromatography? That's what he's telling you to explain. So I want to explain how we do chromatography. Remember, in order to separate a sample into its different constituents, what do we do? Draw a baseline in pencil near the bottom of a rectangular chromatography paper. And then we put spots on the dyes on the baseline. And then we put the paper in a beaker containing a small amount of solvent. And the solvent should be below the baseline. Allow the solvent to move up the paper and then remove the paper. Draw a line on the solvent front. Can you see where the solvent front is? Solvent front is where the solvent went up to. And we allow the paper to dry and determine how many spots for each sample. The diagram shows the positions of some elements in part of the periodic table. Give the symbol of a metal from the diagram. Can you see where metals are? You should realize that metals are on the left side of the periodic table. So, sodium, potassium, aluminium, and actually the one he says indium, IN, all of these from group 1 to group 3, including the transition, all of these are metals. So metals are on the left side of the periodic table. Give the symbol of an element from the diagram that forms an acidic oxide. Okay, which ones form acidic oxides? You should realize that non-metals are the ones that form acidic oxides. So which of these are non-metals? Sulfur or chlorine? Remember that Xe or xenon is a non-metal, but it's not reactive at all, so it does not form any oxide. So the ones that form acidic oxides are the reactive non-metals like sulfur and chlorine. Give a similarity in the electron configurations of aluminium and indium. Can you say where aluminium and indium are? They are both in the same group. The ones that are in the same group have the same what? They have the same number of electrons in outer shell. So all of these are in group 3. So both aluminium and indium would have 3 electrons in their outer shell. Explain which elements in the diagram is unreactive. We said which one is unreactive? You should know the one that is in group 0 or group 8. So the xenon is unreactive, and he's saying explain. Don't forget to explain. This is because it has a full outer shell. So it doesn't want to lose or gain electrons. It already has a full outer shell. A teacher adds a small piece of sodium to a glass trough containing what? Remember what's a trough? A trough is a wide beaker, a big beaker or a wide beaker. A teacher adds a small piece of sodium to a glass trough containing water and universal indicator. The universal indicator changes color. The equation for the reaction is this. Remember, when I put sodium in water, sodium is a very reactive metal. It reacts with cold water, and when it reacts with cold water, it forms the hydroxide. So sodium will form sodium hydroxide plus hydrogen. Explain the final color of the universal indicator. Do you remember the colors of the universal indicator paper? The universal indicator, we said, if it's neutral, pH 7, it's green. If it is a strong acid or a strong base, the colors are like litmus. So strong acid is red and strong base is blue. Now, which one do we have? We have sodium hydroxide in the solution. What is sodium hydroxide? It's a strong base, so the indicator, universal indicator, will turn blue because sodium hydroxide that is formed is an alkaline solution, or it's a strong base. The teacher repeats the experiments with potassium instead of sodium. First of all, is potassium more reactive or less reactive? If you remember, if you look at the periodic table, you find that potassium is below sodium. Potassium is more reactive. So if we put sodium in water, what happens? Can you see? Remember, when we put sodium in water, the sodium will float. It gives off bubbles of hydrogen gas, which may catch fire. What if I put potassium? Now, potassium will be more vigorous and it will catch fire. And when it catches fire, potassium gives a lilac flame when it is burnt. So what is similar in both of them is that both of them are from group 1, so both of them will float, and both of them will form bubbles of gas because both will give hydrogen gas. The difference between them is that potassium is more vigorous. Remember, potassium is more reactive metal, so it gives more vigorous fizzing, and it will form a lilac flame. You remember the flame test for potassium? It gives a lilac flame. The reaction with sodium produces 0.036 grams of hydrogen gas. 1 mole of hydrogen gas contains 6 times 10 to the 23 molecules. Remember this number we called Avogadro's number. 1 mole of any gas contains the Avogadro's number, which is 6 times 10 to the power 23 molecules. Calculate the number of molecules of hydrogen gas produced in the reaction with sodium. So he says the reaction with sodium produces 0.036 grams. So that is the mass of hydrogen gas. Now, in order to get number of molecules, I need first to get number of moles. How do I get number of moles? I have 0.036 grams, which is mass. So I use the equation that says number of moles is mass over molecular mass. Of course, we're talking about hydrogen gas. Hydrogen gas is H2. It's diatomic. And each hydrogen has a mass of 1. So the MR for H2 is 2. Number of moles is the mass over the molecular mass. This gives me the number of moles of hydrogen. He wants number of molecules. How do we get number of molecules? It is the number of moles times the Avogadro's number. We know that 1 mole contains 6 times 10 to the 23. So the 0.018 will contain how much? You multiply by that number, you get a certain number of molecules. So this is 1.0836 times 10 to the 22 molecules. He wants it in 2 significant figures. Please do not leave it with all these significant figures. He wants only 2, so your final answer must be 1.1. Please round up correctly. 1.08 is not 1.0, it's 1.1. 1.1 times 10 to the 22. You should know how to round up a number. Okay, question 5 says this question is about metal carbonates. When heated, some metal carbonates decompose to form a metal oxide and carbon dioxide gas. A student is given 3 solid metal carbonates, a timer, some lime water, and this apparatus. Describe a method the student can use to find out which metal carbonate decomposes fastest. Do you remember this kind of experiments? We have the metal carbonate and we have lime water. And he says that when the metal carbonate decomposes, it forms carbon dioxide gas. So what should I do to determine which of the 3 different metal carbonates is faster? Well, I should weigh a certain mass of the carbonate, let's say 5 grams of the carbonate, put it into the boiling tube, put a certain volume of lime water in the test tube. So I have a specific volume, let's say 10 centimeter cubes, for example, of lime water. Then I'm going to heat the carbonate and determine the time taken for what? Remember that lime water turns milky when carbon dioxide passes through it. So I heat the carbonate and determine the time taken for the lime water to turn milky. Then I can repeat the same thing with the same mass of the other carbonate. So I weigh 5 grams again of the other carbonate with using the same volume of lime water. And the one that takes less time is the one that decomposes fastest. Remember, if a rate is fast, a reaction is fast, it takes less time. So the one that takes less time decomposes fastest. This is how you explain it. A student is given a solid metal carbonate with the formula XCO3. X represents the symbol of a group 2, so we should know we're looking at group 2 metals. A student uses this apparatus to heat a sample of XCO3. So the problem is I don't know what X is. Until it all decomposes, the equation for the decomposition is this. Of course, if we have a metal carbonate, it gives the oxide plus carbon dioxide. The student records the mass of XCO3 and the mass of the carbon dioxide that escapes through the cotton wool plug. And these are the student's results. Now, give a reason why the student uses a cotton wool plug. We are heating the carbonate. Should I close the test tube completely? I cannot do that because I want the CO2 to escape. I want the gas to go out. So I cannot close it with what we call a bung. Okay, why not leave it open without any cover? Because If I leave it without any cover, then I may lose some of my solid. So I have the cotton wool to allow the gas to escape but prevent any loss of solid. Remember, when you're heating a solid, some of it may go out with the vapors or something. I don't want to lose the solid. Calculate the amount in moles of carbon dioxide produced. How do we get number of moles of carbon dioxide? What does he give me about carbon dioxide? He gives me the mass of carbon dioxide. He's saying the mass of carbon dioxide is 2.2 grams. Then I can get number of moles by mass over molecular mass. The mass is 2.2 and he already gives me the molecular mass, so I don't have to sit down and calculate carbon plus 2 oxygens is how much. So it is 44 and I get the number of moles of carbon dioxide. Then he says use the equation to determine the amount in moles of X carbonate that decomposed. Well, let's look at this equation. This is the equation we had. X carbonate gives XO plus CO2. That means 1 mole of X carbonate gives 1 mole of CO2. And that tells me that the number of moles of CO2 is the same as the number of moles of XCO3. So if I'm looking at number of moles, it is the same as the number of moles of the carbon dioxide that we just calculated. Then he says use the mass of XCO3 and the answer to B3 to calculate the relative formula mass of XCO3. Remember that the problem is I don't know what is X. So I cannot get MR directly. I cannot say carbon is 12 plus oxygen is 16 times 3 plus X. I don't know what's X. So I need to get the MR in a different way. How do we get MR? Which equation has MR in it? You should know. He says the mass of X carbonate is this. I can use the mass to get MR. MR is mass over number of moles. Remember, number of moles is mass over molecular mass. So molecular mass is mass over number of moles. He gives me the mass 7.4. We got the number of moles as 0.05, and that gives me an MR of 148. And that means the total masses of X plus carbon plus 3 times 16 for oxygen, all of them total is 148. Can we get what is X? The X plus the carbon, which is 12, plus I have 3 oxygen, 16 times 3. All of this is 148. If you solve for X, then you find that X is 88. Now, X is the mass number of 88 is the mass number of X. So what is the identity of X? I look at the periodic table and he told me that it was in group 2. So I look in group 2, which one has a mass number of 88? Looking at the periodic table, is the mass number the big one or the small one? You should know that the mass number is the big one. So I find that strontium is the one that has a mass number of 88. Silicon hydride and silicon dioxide both contain covalent bonds, but they have different structures. Describe the forces of attraction in a covalent bond. Now, if he tells me, explain what is a covalent bond. Do you remember what's a covalent bond? In a covalent bond, we're sharing electrons between 2 atoms. And we said the covalent bond is the strong attraction forces between the bonding pair of electrons or the shared pair of electrons and the positive nuclei of the atoms. So each atom has a positive nucleus. They're sharing a pair of electrons. There is a strong attraction between the shared electrons and the positive nucleus of each atom. This is what we call a covalent bond. Please don't say it's a bond between 2 nonmetals. That's not the definition of covalent bond. Okay, complete the diagram to show the outer shell electrons in a molecule of silicon hydride. So we want only outer shell electrons. If you look at silicon, silicon is in group 4. That means it has 4 electrons. It needs 4 more electrons. So each of these hydrogens will share 1 electron from hydrogen, 1 electron from the silicon. So this is what we call the dot and cross diagram for silicon hydride. The diagram represents part of the structure of silicon dioxide. State how the diagram shows that the atom labeled A is oxygen, not silicon. How do we know that A is oxygen? If you look at the periodic table, oxygen is in group 6. That means it has 6 electrons in its outermost shell. That means it needs how many? It needs 2. So any oxygen atom has to form 2 bonds. And the atom in A is having only 2 bonds. But if you look at silicon, the periodic table, it's in group 4. Group 4 means it needs to have 4 bonds, or it has 4 electrons and it needs to have 4 more. So it has to have 4 bonds. So the ones that have 4 bonds, these are silicon. Those dark balls are silicon because they're forming 4 bonds. The gray ones, like A, are oxygen because they're forming only 2 bonds. Silicon hydride has a simple molecular structure, while silicon dioxide has the same type of structure as diamond. Do you remember the structure of diamond? Explain why silicon dioxide has a much higher melting point than silicon hydride. Okay, so he's saying silicon hydride has simple molecular structure. If I tell you, that means it has low melting point. Why does it have low melting point? You should know that any simple molecular structure has weak attraction forces between molecules, and that needs a small amount of energy to be broken. So anything that has simple molecular structure will have low melting point, weak attraction forces between molecules that need a small amount of energy to be broken. While silicon dioxide is like diamond. Do you know what's the structure of diamond? It's a giant 3-dimensional structure with many strong covalent bonds, and that these need a lot of energy to be broken. So anything that has a giant 3-dimensional structure, diamond or silicon dioxide, both have strong covalent bonds, many strong covalent bonds that need a lot of energy to be broken. Then he says silicon hydride reacts with oxygen to form silicon dioxide and what? Write a chemical equation for the reaction. So he already told me that silicon hydride, that's SiH4. Now he's reacting it with what? With oxygen. Remember that oxygen is diatomic, so it has to be O2. To give what? Silicon dioxide. Silicon dioxide means I have 2 oxygens for each silicon, so SiO2. And water, of course, is H2O. Please, when you write these equations, do not forget to balance. I cannot leave it and go. I have to balance it. How do we balance? We count the atoms before and after the arrow, and we increase the one that is less. So how many silicon before the arrow? I have 1 silicon before the arrow. How many silicon after the arrow? I have 1. So that's balanced so far. How many hydrogens before the arrow? I have 4. How many hydrogens after the arrow? I have only 2, so I need to put 2, so that 2 times 2 will be 4 hydrogens after the arrow. Now, how many oxygens before the arrow? I have 2 oxygens before the arrow. Now, after the arrow, I have how many? I have 2 from the SiO2, and I have another 2 from the 2 water. So that means after the arrow, I have 4 oxygens. So I need to put 2 here so that it's 2 times 2. So it's 4 oxygens. Please remember to balance. The diagram shows some important conversion processes used in the oil industry. Describe how kerosene is produced from crude oil. So when we have crude oil, he says the first process will give me kerosene. What do we do to crude oil to separate it into different fractions? Remember that we do what we call fractional distillation. So that what happens is the crude oil is heated and vaporized, and then it goes into a fractionating column where it is cooled and condensed at different boiling points. So these fractions are separated based on difference in boiling point, The ones that have lower number of carbons have lower boiling points. So they condense at the top of the tower. As we go down in the fractionating column, the fractions have higher and higher boiling points. So this is how we separate components of crude oil, or what we call petroleum. Then he says C12H26 is present in kerosene. In process 2, C12H26 is cracked to produce 2 molecules of ethene and 1 molecule of another hydrocarbon. First of all, do you remember what is cracking? Cracking is the breakdown of long chain hydrocarbons into shorter chains. So we're breaking down the C12H26 into 2 molecules of ethene, which is C2H4, plus what? Of course, the rest of the C12 and the rest of the H26, that is what we're looking for. So if I'm starting with C12, I removed from it 4 carbons, so I'm left with how many carbons? I'm left with 8. And the hydrogens were 26. I removed 2 times 4, so I removed 8 from the 26. I'm left with H18. So the C8H18 is just the rest of the C12 and the H26. Explain why cracking is a useful process in the oil industry. Why is cracking useful? You have to remember, cracking, we said, breaks down the long chains into shorter chains. So these shorter chains are usually more flammable, more in demand, higher price, so more profitable economically. We also get things like ethene or different alkenes, and these are used to make polymers. So if I'm making ethene from cracking, I use it to make polymers, and I can use it to make ethanol, which is an important product also. This is the equation for one of the reactions that may occur during process 3. So this is an alkene, and he's adding chlorine to give the dichloro product. Remember, alkenes, when they react with halogens, this is called an addition reaction. Alkenes do addition reactions. Complete the equation for the polymerization of chloroethene. Now, if I am forming a polymer, how do we draw the polymer? Remember, I'm starting with a double bond in the middle. I will end up with a single bond instead of the double bond, and then I have a bond on both sides to join them to other molecules like them, and all of this is repeated n times. So this is how you draw the polymer from the monomer. The monomer has a double bond. You copy exactly as it is, but instead of the double bond, you put a single bond, a bond on the right and a bond on the left, to connect it to other molecules before and after it. And this unit is repeated many times, so we write an N to indicate that this is repeated N times. Explain why the disposal of polymers such as polychloroethene is difficult. What is the problem with disposal of polymers? You should remember that polymers accumulate in dump sites when we throw. You remember that polymers means plastics. Plastics are polymers. So when we throw plastics or when we throw polymers, they accumulate in the dump sites. Why do they accumulate? Because they're not broken down by bacteria. So we say they are non-biodegradable. And even if I decide to burn them, burning them releases toxic gases. So the problem with polymers is that they are non-biodegradable, so they do not break down in dump sites or in landfills, and they accumulate. And then when burnt, they release toxic gases. Okay, this question is about exothermic reactions. A student uses this apparatus to measure the temperature increase when an excess of zinc powder is added to copper sulfate solution. Complete the word equation. So if we react zinc with copper sulfate, what do you get? Remember that zinc is a more reactive metal than copper. It will displace it, and it will give zinc sulfate plus copper. He wants words, so you complete it in words. Please do not complete it in symbols. If we start with word, we end with word. If we start with symbols, we end with symbols. Give a reason why the student uses a polystyrene cup inside a glass beaker. Can you see the polystyrene cup? You know that polystyrene cup is plastic cup, and polystyrene is um, an insulator, so it will not lose heat to the surroundings. So we usually do any of the experiments in which we need to measure temperature. We do this in a polystyrene cup because it's an insulator, so it prevents loss of heat to the surroundings. State why zinc reacts with copper sulfate. We said, why does zinc react with copper sulfate? Zinc is more reactive than copper and can displace it. The temperature at the start of the reaction is this. The temperature at the end of the reaction is this. Calculate the heat energy change for the reaction. Okay, what is the heat energy change? How do we do that? Remember, we did this experiment with a polystyrene cup. We had a certain amount of copper sulfate solution, and he measured the increase in temperature when we added zinc. So to get the heat energy change, you should remember that heat energy change, that is Q. Q is equal to mc delta T. What is M? M is the mass of the solution. So I have 75 grams of copper sulfate. That is my M. What is C? This is a given number. It's 4.2 times the temperature change. So you're going to subtract the temperatures from each other so that you get the temperature change. All of this gives you the heat energy change in joules. Remember that Q comes out in joules. Then he says the reaction between zinc and silver nitrate is exothermic. A mass of 0.65 grams is added to silver nitrate, and the heat energy change is 800 joules. So he did this experiment, and he got that Q for this experiment is 800 joules. Calculate the molar enthalpy change. Calculate delta H. Do you know how to get delta H from Q? You should remember that delta H is Q over N, number of moles. So I need to get number of moles of zinc. Number of moles is mass over molecular mass. Again, I'm reminding you, the molecular mass is the big number. So molecular mass of zinc is 65. So we get number of moles of zinc. Then the delta H is the Q over N. He gives me the Q as 800 joules. We want the delta H in kilojoules. So you need to divide that by 1,000. So that is 0.8 kilojoules. Divided by the number of moles that we got. Remember that delta H must have a sign. Now, how do we decide on the sign? Why did I write a minus sign? Because the first statement up there says the reaction between zinc and silver nitrate is what? Exothermic. When a reaction is exothermic, that means that delta H is a negative number. So it's minus 80 kilojoules per mole. This is the ionic equation for the reaction between zinc and silver nitrate. Explain in terms of electrons why this is a redox reaction. What does redox reaction mean? It means in my reaction, I must have an oxidation and a reduction. So you have to tell me that it is redox because it involves both oxidation and reduction. Okay, where is the oxidation? Where is the reduction? He's saying explain. Zinc changed into zinc 2 plus. In order to change into zinc 2 plus, it lost electrons or increase in oxidation number. So zinc to zinc 2 plus, that is oxidation. Then Ag plus to Ag, what happened? The Ag plus gained electrons, or there is a decrease in oxidation number, so that is reduction. This question is about rates of reaction. A student uses this method to investigate the rate of reaction between iron 3 nitrate and sodium thiosulfate solution. Remember, for all of these questions, when you have a big introduction like this, please go through it very quickly and then just to get an idea of what he's doing and then continue to the question. Pour 50 centimeter cubed of iron 3 nitrate into a flask, add 1 drop of catalyst, add 50 centimeter cubed of sodium thiosulfate, record the time for the mixture to become colored. The student repeats the method using different catalysts. So what he's doing is he's repeating the experiment using different catalysts. And he gives you the results. And the question now is, explain which is the best catalyst for the reaction. Looking at the table, which one is the best catalyst? Remember, what's a catalyst? It's a substance that speeds up a reaction. Now, when it speeds up a reaction, that means it makes the reaction faster. That means it takes more time or less time. If a reaction is faster, it should take less time. So if I'm looking for the best catalyst, I'm looking for the one that took the least time, the smallest time. So copper sulfate, because this is the one that took the least time. So this is a more effective catalyst, make the reaction faster. Explain how a catalyst increases the rate of a reaction. What does a catalyst do? You should remember that for any reaction, for example, exothermic and endothermic, you have a certain energy of activation or activation energy. Where is the activation energy? It's the difference in energy between the reactants and the top of that hill there. Okay? So the higher the activation energy, the more difficult the reaction is. So if a reaction does not have a catalyst, then the activation energy is high, whether we're talking about exo or endo. But if I'm using a catalyst, what happens to the activation energy? The activation energy is lower. This is because a catalyst provides, this is how we explain, an alternative pathway for the reaction. So it makes the reaction happen in a different way that lowers the activation energy. So it provides an alternative pathway for the reaction that lowers the activation energy. And remember, a catalyst is the only factor that will lower activation energy. The rate of a reaction can also be altered by changing the temperature or by changing concentration of solutions. Explain using the particle collision theory how increasing the temperature affects the rate. Why do we say that when we increase the temperature, the rate is faster? You should know at higher temperature, particles gain more kinetic energy, move faster, so there is more frequent collisions. More of the molecules have energy higher than activation energy, so the reaction rate is faster. Remember, you're supposed to explain and you're supposed to mention how it affects the rate. So you have to mention that when we increase the temperature, first of all, the reaction rate is faster. Now, why is it faster? Particles gain more kinetic energy, move faster, more frequent collisions, more of the molecules have energy higher than activation energy. Explain why using a solution of lower concentration decreases the rate. If I have lower concentration, what happens? Here he's already telling me it will decrease the rate, so all I need to do is explain, because if I have lower concentration, that means I have less particles, so less collisions per unit time. A student investigates how the electrical conductivity changes as dilute sulfuric acid is added to barium hydroxide solution. So he added 50 centimeter cubed of barium hydroxide to a beaker. He measures the electrical conductivity of the solution. He added 10 centimeter cubed of dilute sulfuric acid, stare, measure the electrical conductivity, and then repeat using more and more of the acid until a total of 100 centimeter cubed of acid has been added. The table shows the results. And now he wants me to, first of all, name a piece of apparatus the student could use to add 10.0 centimeter cubed of dilute acid. Remember, when we want to add something, a volume exactly 10.0, I can use a pipette Or I can tell him burette. Burette also can be. Then he says, plot the student's results. Do you know how to plot? You should plot using small x's. So if you plot, this is what they look like. Now, he's saying, ignoring the anomalous result, draw two lines of best fit. Please, before you join the points, check and see which instructions he's giving you on how to join the points. So here he's saying, draw two lines of best fit, making sure that the two lines cross. So obviously these are the two lines. This that is far away from the line, this is the one he's referring to as the anomalous result. It's a wrong result, so you don't include it in the line. Give the trend shown on the graph for the first 50 centimeter cubed of acid. If you notice, for the first 50 centimeter cubed of acid, as the volume of acid increases, the electrical conductivity decreases. This was the graph that we had. As for the first 50 centimeter cubed of acid, so down there, total volume of acid from 0 to 50, as I increase the volume of acid, the electrical conductivity decreases. Then he says, suggest a mistake the students could have made to cause this anomalous result. So this result that is far from the line, what mistake do you think the students could have made? Well, he probably added less than what he should. So at that point, he was supposed to add 20 centimeter cubed of acid. He probably added less, and that's why his answer is not on the line. Or he did not stir the solution properly. This is the equation for the reaction. When 50 centimeter cubed of dilute sulfuric acid has been added, only barium sulfate and water are present. Can you see the barium sulfate? The barium sulfate is a solid. Now, explain why this mixture does not conduct electricity. Refer to the type of bonding in barium sulfate and in water. So in my product, what do I have? I have barium sulfate solid and I have water. And he's telling me this does not conduct electricity. Do you understand why? Well, barium sulfate is ionic. And you should realize that ionic compounds do not conduct electricity when solid. We said they conduct electricity only when molten or in solution, so that the ions will be free to move. Water. Why is it that the water, as it is, does not conduct electricity? Water is a covalent compound. And we should know that covalent compounds do not conduct electricity. Name a technique the student could use to separate barium sulfate from the mixture. I have a solid in the mixture. What do I use to separate it? I use filtration. Okay. This question is about the reduction of tungsten oxide, WO3. A teacher uses this apparatus to reduce tungsten oxide. This is the teacher's method. Record the mass of a weighing boat. A weighing boat is just a small apparatus that we use for weighing. Add tungsten oxide, record the mass again, heat the weighing boat and tungsten oxide strongly for 2 minutes and then allow to cool. Record the mass of the weighing boat and its contents. And the first question says, complete the equation by adding the state symbols. So, what do you think is the state symbol of the tungsten oxide? This is something that he was weighing in a weighing boat, so obviously this is a solid. Hydrogen is a gas. What is tungsten alone? Tungsten is a metal, so it's a solid. And water, of course, is a liquid, or you could regard it as water vapor. In that case, you can write G. Give an addition to the method to check that the tungsten oxide has been completely reduced. Okay, how do I know that the reaction has finished? Remember that when we do a reaction like this, where we're weighing the mass at the beginning and then we want to weigh it at the end, what we do is we need to repeat this process until the mass is constant. So we repeat the process of heating and cooling until what we call constant mass. The table shows the teacher's results. Use the teacher's results to show that the empirical formula of tungsten oxide is WO3. Okay, how do I get that the empirical formula is WO3? Well, we need the masses of the tungsten and the oxygen. So what is the mass of the tungsten? It is the difference between the weighing boat and the weighing boat and tungsten. So weighing boat and tungsten minus the weighing boat alone, that is the mass of tungsten. Now I want the mass of oxygen. How do I get the mass of oxygen? It is the mass of the tungsten oxide and weighing boat minus the tungsten alone and weighing boat. So 1704 minus 16.56. This gives me mass of oxygen. Then how do we calculate empirical formula? In the normal way, we put the masses of each one. What do we do first? Divide by the mass number of each of them. This gives you a certain number, and then you divide by the smallest. So you find that the ratio is 1 to 3, and that means that the empirical formula is WO3. Then he says the teacher wears eye protection and the lab coat during the experiment. Give one other safety precaution the teacher should take. Now, when he says this, so just a safety precaution, I go back to the experiment. What was he using? Well, he's using hydrogen gas, and hydrogen gas is flammable and so on. If we're doing an experiment that has a gas, I have to do it in a fume cupboard. So I tell him, do the experiment in a fume cupboard. In industry, tungsten oxide is reduced on a large scale using hydrogen. The percentage yield of tungsten is 73.5%. So he's saying when they do this experiment, he gets only 73.5% of what he's supposed to get. Then this is the equation for the reaction. Calculate the mass in tons of tungsten that is produced when I'm starting with 2,784 tons of tungsten oxide with reacting with excess hydrogen. He tells me that the ton is 10 to the 6 grams, and we should actually know that a ton is 10 to the 6 grams, and you should know that we need to work in grams, not in tons. Okay, so he's saying he started with 2,784 tons of tungsten oxide. That is the information he gives me. I use it to get number of moles. So number of moles is mass over molecular mass of the WO3. This comes out to a certain number of moles. Remember, we're working in grams, so I multiply this by 10 to the 6 in order to put it into the equation. Then, from the number of moles of tungsten oxide, I look at the equation. What is he asking me about? He's saying calculate the mass in tons of tungsten. So I want the mass of W. I look at the equation. I find that the number of moles of WO3 is the same as number of moles of W. So number of moles of tungsten will be the same number of moles. Now he's asking for mass. How do I get mass? Mass is the number of moles times the MR of tungsten. But then this will give me the actual theoretical yield. He says that he actually got only 73.5% of that. So that means that I have this amount in grams. He wants the mass in tons. So this is this number in tons. Are we okay with all of this? I hope this was useful. This was the last question. Please practice all of this and revise all of this, and I hope you do well in your exam. Thank you for listening.